So good afternoon, everyone, and welcome to today's seminar titled Simulating the Strong Force Using Large-Scale High-Performance Computing, State-of-the-Art and Future Directions by Machine Learning. Our speaker today is Dr. Jakob Finker-Rath, who is currently a research scientist at CaSToRC and leads the high-level support team for academic projects of the National Competence Center in High-Performance Computing of Cyprus, which is being implemented within the EuroCC project. He received his PhD at the University of Wuppertal in 2015 in theoretical particle physics on stochastic methods for the calculation of the fermion determinant. Since 2015, he works at CaSToRC as a computational scientist and is a member of the extended Twisted Mass collaboration. Within this collaboration, he leads the simulation effort by tuning and generating cutting-edge lattice quantum chromodynamics gauge assembles at physical light, strange, and charm quark masses. These large-scale Markov chain Monte Carlo simulations utilize large computer time allocations on HPC systems around the world like SuperMOOC, Quark, and Frontera. Jakob, thanks for being our speaker this afternoon. We look forward to your talk.
Yeah, thank you very much, Stelios, for the introduction. Actually, can I walk through the room, or I still need to stay here? I guess I still have to stay here, no? Okay. Okay.
Ideally there to listen to you.
Yes, right. I just recognize that I don't have a microphone. So, okay, let's take a look to the content of the talk. So basically, it's in three parts. So first of all, I will give a basic introduction to fundamental physics and our methods, how we basically start to do our calculations. Then I will basically talk about hybrid Monte Carlo simulations, about the algorithm itself. Basically, I will use a cost formula to go through all these different types of algorithms. So the inversions, we need to invert the Dirac operator. Then we have numerical integrators, which we have to tune. And then at the end of the talk, a larger section, basically at the end, on autocorrelation and how one can try to come over so-called topological freezing by using machine learning methods. Okay, so what does this mean, fundamental physics? I mean, maybe as a starting point, one can look at the length scale, or the meter scale. And take a look where basically the physics takes place. So it's fundamental physics. So it's basically the fundament of all our physics. So if you take a look, I mean, this is basically the scale in meter. So here we have 1 meter. And this is basically the upper end, the size of the universe. And the lower end is basically the Planck scale. And if we basically go down from meter towards smaller and smaller, we will end up at the standard model of particle physics. So maybe just as a starting point, so our daily life is more or less in this magnitude, so 6 magnitudes between kilometers towards millimeter, where maybe millimeter is the size of an ant. If you go down, I mean, if you basically zoom in into the world, into the tiny world, you end up basically here at the micrometer scale, where we have our first microprocessors from 1971, where the transistor size were 10 micrometers. And nowadays we are basically in the nanometer scale for these transistors, where, for example, this chip here, the AMD MI250, is basically the transistor sizes of 5 nanometers. And this is also the scale where the bacteria, the coronavirus are living, and at the nanometer scale, you have these larger molecule structures like DNA. So if you go then one down, we end up at the angstrom scale, where we basically have the size of the atoms. And then going basically, this is the size of the atom is basically given by the orbital diameter of the electrons. And then we need to go 5 additional magnitudes downwards to the femtometer scale, where the standard model of particle physics basically is living. So quite basically on the fundament of this scale. So how we do this, basically, this is a SketchUp of the Standard Model of particle physics. Here, what we're doing, our scale is not in meters. So we are switching the scale to energies. So basically, we can in the inversion. I mean, it's basically so this going towards higher energies, going towards smaller scales. Okay, so what we have basically in the model in particle physics and in the standard model of particle physics, we have fermions, particles, which are interacting via bosons. And the bosons are basically given, for example, you basically know it the most. I mean, if you look at this picture here, maybe it's come to you see basically what you should know is the electron here. Which is interacting via the electromagnetic interaction via photons. The mass of the electron is around 500 kilo electron volt. And in the standard model of particle physics, we know that there have basically heavier partners. There is a heavier so-called a second family where we know that there's lepton, which is heavier, which is called the muon, which is around 100 MeV. And then there's additionally a third family of the same basically type, which is a tau lepton. And these leptons are interacting via the photons and their weak interaction. This is the interaction is carried by the W and Z bosons. And additionally, I mean, you see it basically here. Additionally, we have the cores of the atoms and are basically formed by quarks and gluons. And so they're basically, I put them here on this style. So the lightest quarks and gluons, the lightest quarks which you know are the up and down quarks, which are around 5 MeV of the mass of them. And they also have basically heavier partners. There are existing heavier families, which is the strange quark and the charm quark, and then even more heavier ones, which are the bottom quark and the top. And the quarks are not only interacting via their weak and their electromagnetic interaction, they're also interacting via the strong interaction via the gluons, which also carries strong charges. Okay, and last but not least, what makes the standard model complete is the Higgs boson, which is basically at 125 GeV, which is giving masses to these particles. And as we also discussed yesterday, it was detected around almost 10 years ago at the LHC, which has a energy. I mean, there we collide photons made of down quarks and up quarks and gluons on each other with a colliding energy of around 10 tera electron volt. And basically, we know there are higher energy possible in our universe. So we basically we have events in the cosmic. If a cosmic particle hits basically the atmosphere, and there are events which have much higher energies than we generate at the Okay, so what we actually now doing is or what we are doing on here at CaSToRC, we are simulating the strong interaction. So we are basically taking out the quarks and the gluons and simulating them using supercomputers. While basically the other interactions are one can use perturbation theory to add these effects if one needs them for their predictions. So okay, let's take a look basically how this is done. So we have basically the experiments, which we already saw from the colliders, where we basically measure where we collide particles on each other, and then we can measure the products of this collision and interpret them as basically as measurements. And this we can compare with the theory. So we basically know how the theory is working based on the standard model based on the Lagrangian of the standard model, which I just briefly try to introduce with all these particles. So basically the particles appears here as fields. For example, the fermions, so the electrons and quarks appears here as a size. The gluons or the weak interaction particles W, Z bosons, W and Z bosons appears here in this F menus, and the Higgs is given by this phi. So one can use perturbation theory to make predictions and then compare this with experiments. However, going to the strong interaction, which basically forms these hadrons, the protons and neutrons, with the quarks and gluons, this one cannot basically expand anymore around the strong coupling constant, and we need to basically put these equations on the computer. So this is basically the other aspect. We can basically discretize the theory, put it on the computer, and make also prediction and compare this to the experiments. Okay, so the starting point of our calculation is the Feynman path integral, which is basically this lengthy equation here. So what you see is basically we have here the Boltzmann factor. This comes with e to the power minus the gauge action. And then we have an integral over all our points, or the degrees of freedom. So the U's are containing the gauge lengths, basically the gluonic degrees of freedoms, while the quarks are already integrated out. So the degrees of freedom of the quarks are contained basically in this determinant here. So what we do is basically we discretize the action and put them on the lattice. And then we have this lattice spacing, and then we need to solve this integral for different lattice spacing that we can then extrapolate towards the continuum limit towards A equal to 0. Okay. So what is the problem? I mean, so basically this is, I mean, we can basically calculate observables here by evaluating this integral. And the problem is that we have a lot of degrees of freedom. So this is a high dimensional integral. And this standard method to calculate or to get some values out of this is to using Monte Carlo simulations. So the basic idea is to do a Markov chain Monte Carlo simulation of this using the Boltzmann weight, which is given here. So one samples field configuration with this weight here. And then in 2 steps, basically one proposes a new gauge configuration based on the old one, and then one has an accept reject step. And then one samples this important gauge field configuration, and on this one can calculate the observables, and then one can get an error and can compare this to the experiment. So let me introduce the main algorithm which we are using to do this Monte Carlo Markov chain Monte Carlo simulations, which is a hybrid Monte Carlo algorithm. And this is based on Hamilton's equation. So basically we have a description. I mean, the idea is we start from a configuration and we want to generate a new configuration. So we have to find a procedure to generate this new configuration. And a good way is to just use Hamilton's equation to develop or to integrate basically the degrees of freedom through the phase space. This can be done with these equations. And basically, because we are doing this numerically, after each trajectory, we have some numerical errors, and which we don't want. So what we do, we correct with the correct with an accept direction step by taking basically the Hamiltonian at the end of the trajectory into account minus the Hamiltonian at the beginning of the trajectory. And if this basically filters out our numerical errors and makes this procedure exact. Okay, so what you're basically doing is as I already said, we basically integrating this guy here. So what we have to do for this, we have to calculate this force. So we have to calculate the derivative of the gauge lengths with respect to the Hamiltonian. For this, we have to invert the Dirac operator, because I just jumped it, but basically the Dirac operator appears as an inverse in this weight. So it appears as an inverse in the Hamiltonian. So for the force, we need to invert the Dirac operator. And then we need several steps for each trajectory. So basically the cost for these simulations are coming from the force computation and from the number of costs we need to do. And at the end of the day, also we want to have a small error. So we need to do need to do a lot of these steps. So basically this is giving our computational costs. So let me try to go through these different points and illustrate how this how we basically worked on these different things to improve our simulation and to generate then really large ensembles at physical quark masses. Okay, so first of all, we took a look to the inversion of the Dirac operator. Okay, so basically, I have here a small video of thermalization phase of the Schwinger model and HMC. Basically, you start as a random field configuration, and then you thermalize. And here, what I basically show is from the slope of this correlator, which I measure here, one can calculate the pion mass. So let me just play it, and then so what you see is basically here's a spectrum of the Dirac operator. And in the thermalization phase, the spectrum moves closer and closer to 0, which means that the condition number of the matrix of the Dirac operator gets larger, which means that our inversions, our linear solver becomes more expensive during this time. Okay. So and I mean yeah. Okay. So to calculate the force, we need to basically solve this equation the whole time during the trajectory. So for an unknown vector x, and D is a large sparse matrix. So this basically all our computation goes into solving this equation rapidly. So a basic method is using iterative solvers for this Krylov, so-called Krylov methods, by basically generating this, multiplying the right-hand side with D for several times, and then I can solve in a smaller space, of course, Krylov space, to get an iterate, which is then basically a solution for this equation. So we are interested in basically going to very small quark masses, which are basically representing physical quark masses. And in doing so, as I previously showed in the video, the small eigenvalues become smaller and smaller, which means the time to, the inversion cost increases more and more. So for this conjugate gradient solver, you see the cost basically grows with 1 over this quark mass, which is here, this parameter mu. And so we basically, by measuring the dependency on mu of this conjugate gradient solver, we get this cost formula for this inverter. So basically, I fit it here with the coefficient b and a, and then I get this ratio b over a is around 0.04. But okay, this means basically that going to very small quark masses makes the simulation very expensive because, as you see, you start from, you need around 10 to the power 3 seconds for the inversion. There are basically better ways to do this. And one of these ways, which we are basically worked on here at the Institute, are based on multi-grid solvers. So Simone worked on this during his PhD. This is the idea is basically to separate the different eigenmodes. So basically to have a preconditioner for the solve and to project the small eigenmodes, which are very expensive, to a smaller so-called coarse grid operator. And then this coarse grid operator is computationally less intensive because it's smaller. And then due to that, you can you can converge faster to your solution. So this is basically shown here, the multi-grid solver, which we are using in our simulation, DDR-FMG, compared it's actually running on a CPU cluster here on Lumi, actually, compared to GPU implemented for GPUs conjugation solver with a mixed precision approach. And you see basically that you very fast outperform this conjugate gradient solver. And again, if you measure now these two coefficients, I mean, if you fit this here with this linear approach, 1/mu, you get a ratio of 0.01. So you basically get rid of the mass dependency of your simulation. So basically going to the physical point, the solver cost doesn't really increase a lot. Okay, so what we can now do, we can go back to the cost formula of our HMC. So if you remember, one thing was given by the cost for the solver. So to basically calculate the forces during the trajectory, then the number of steps which you have to do, and from our improvements from the multi-bit solver, we got rid of basically the mass dependence and only have the volume dependency. I actually forgot to mention it, but basically what you have here, you have to multiply this vector with a matrix, and the matrix scales with the volume, so you automatically get this volume dependency from the pure computation. Okay. And basically, if you compare now the CG to the mg, mu at the physical point is around 0.007, which means for the CG, this 1/mu is dominating, while for the multi-grid at the physical point, the one is still dominant. Okay, so this was basically our first improvements of the simulation. We could decrease our computational time for one trajectory by an order of 10. So this enabled us to simulate our first physical point lattice at the large size of empire around 4, going from Euclidean to super. And now the question is, let's take a look to the steps. So I didn't talk about the steps. So we can basically now try to use higher order integrators for integrating our physical degrees of freedom through the phase space. So the most basic one for doing this is a leapfrog. Basically, you want to integrate your gauge lengths and your conjugate momenta to a time which is later. So in this case, one step. You can do this by first updating your momentas by calculating the force term, and then using these momentas to update your gauge lengths. And due to that, you have these jumps, which is then, if you do this several times, you have something like a frog which is jumping from the gauge lengths to the momentas and vice versa. So due to that, you have this name. While this is the most simplest one, and this is an order, second order. I mean, this scales with, I mean, you make an integration error, which goes with h⁴ in this case. You can use higher order integrators, which have a higher order error. So instead of h⁴, h⁴. And algorithms of this kind are, for example, the second minimum norm scheme force gradient solver, which is basically shown here, which if you see, so what is shown here is basically the variance of the accept reject step, which is if it's this value, it gives you an acceptance rate after each trajectory of a factor of 95%. And you see that this red line here basically outperforms all the other solvers with respect to the number of steps. So h is 1 over the number of steps. Okay, so we can do this. I can do even an additional step by basically introducing additional terms. Basically, they're coming with additional mass terms. And this makes it more complicated to tune, to tune your HMC to an optimal point. So let me first of all say something about this equation. So as we saw, so first of all, we need to I mean, the idea of this hybrid Monte Carlo algorithm is to integrate your physical degrees of freedom through the phase space, and at the end of each trajectory, you to make an accept-reject step. And this accept-reject step has an acceptance rate, and if basically the accept-reject step is done with the difference of the Hamiltonian at the beginning and at the end of the trajectory, and if this delta H, so-called, is distributed normally, not normal, then you have a relation between the acceptance rate and the variance of delta H. So if you know if you know how the variance behaves with all your parameters, you can basically tune. I mean, you want to have an acceptance rate of, let's say, 90%. If you know the variance, you can, say from the beginning, I want to have 90%, and then this automatically, by demanding that you want to have the minimal costs, you get a procedure on how to tune this coefficients. First of all, you need to know for this the variance. So for this, we measured the variance for different for the whole parameter sets, for the whole parameter space, and we come up with an effective model for fitting them. So basically, there are some, in this case, 3 different coefficients in this fit model. So this is rather this fits rather good the variances. Using this model, we can tune our step size for minimal costs. And this is basically given by this formula here. And if you look closer, what you see is basically that, so from this equation, you see that the variances goes with 1 over the number of steps to the power 2n, and 2n is the order of your integrator. So if you want to know the number of steps, so if you put all this together and solve for a number of steps, you get basically this approximation. And if this delta mu is close to mu square, you get rid of the mu dependence. And what you're left with is basically the volume. So you get from the number of steps a volume dependence, which goes with the order of the integrator. So with this knowledge, we can go back to our cost formula and see what happens if we go to a higher order integrator. So basically, the cost formula is now the volume cost from the solver, then the volume which comes from the steps, so which goes with 1 over volume to the power 1 over 2n. So we saw already this improvement by using the multigrid. Now by including a higher order integrator, so a 4th order integrator, we can actually minimize the volume scaling here. So going to larger volumes reduces the cost by using a higher order integrator. And this basically enables us to generate larger volumes. And due to that, we can basically take the continuum limit at the end of the day. So yeah, basically this is this overview here. So what we started with was this ensemble 64 cube at a lattice spacing of 0.08. And due to the improvements which we did by using basically by using the multigrid solver, then by using higher order integrators, we could generate ensembles of larger sizes at smaller lattice spacings. So basically 3 of these. So we have now 3 ensembles at physical quark masses at 3 lattice spacings. And so we can basically take the continuum limit, measuring observables on these 3 lattices, and then take the extrapolate towards a equal to 0. And on the other side, we can control the finite volumes effect, which are coming from the finite lattice by simulating different sizes of lattices at the same point, which is basically shown here. And okay, there are more of these simulations in the production, the smaller lattice spacing and the quarter lattice spacing, which even more, which even decreases further the error. Okay, so let's just briefly look to a result which we did on these ensembles. We can, what I showed you at the third slide, basically the quark masses were on this mass scale. We can measure these numbers using lattice calculations. Actually, to calculate or to measure the quark mass is quite difficult in the ensemble of particle physics, because the quarks are strongly coupling, and usually they're appearing in bounded states. So you cannot get them alone, let's say, and so due to that, it's very difficult to measure the masses in experiment. But actually, in Lattice QCD, the quark masses are input variables, so we can easily get these numbers. Okay, how we do this? We basically measure masses of baryons. Here, in this case, for the strange quark mass, we measured the mass of the omega baryon. And then we do this on different ensembles. So what you here basically see, these 2 points here are the points which are measured on 2 physical point ensembles, while the other ensembles are done where the pion mass, the quark mass, is heavier. But this helps us basically to extrapolate towards the continuum, which is basically this point here. So we did a generalized fit with different lattice spacing, different ensembles to get the strange quark mass here. Okay, so this is basically an overview of these results. And if you look, I mean, there were ETMC results from 2014 compared to using only 2 physical point ensembles. We could basically improve the errors almost by a factor 2 compared to these blue points. While we need to further improve using, I mean, now we have more lattices compared to last year to further improve this value. Okay, so there were basically one missing piece is this statistical error in our cost formula for the HMC. So we discussed basically how we improve the solver, how we can control the number of steps. But basically what I didn't discuss yet was the number of configuration which we are needing to get a reasonable small error. The error is basically usually given in our experience is proportional to the autocorrelation time, the integrated autocorrelation time over the number of configurations. So if this guy here, this autocorrelation time behaves bad, then we need a lot of steps to generate the ensemble size, which we need to have a reasonable small error. And actually this happens in Lattice QCD if you go to the continuum limit. So if you go below 0.05 femtometer, then the autocorrelation, for example, of the topological charge is observable, which we take a look to soon, is basically increasing and quite rapidly, which makes it impossible or not computational, not feasible to simulate for very small lattice spaces. Okay, so this is here an example in case of the Schwinger model. So this is basically now I will discuss a method or an algorithm which basically try to overcome this critical slowing down, to basically try to mild down the autocorrelation, this increase of the autocorrelation, which is going basically here with a coupling constant to the power -6. And in case of QCD, it goes with the power -8 to the power -5. So let's take a look for the Schwinger model. I mean, I did this work in the Schwinger model. To the topological charge. So this is a run. So the Schwinger model is 2-dimensional in this case. The topological charge is a quantized quantity, so it's basically takes integer number, and for the coupling constant, which corresponds to a quite rough lattice spacing, it fluctuates quite well, as you see. While going towards higher beta values, which corresponds to smaller lattice spacing, so beta is 1/a² roughly, you see that the topological charge is freezing out. While for this value here, it's basically has one jump, and then it's freezed out. So it's using HMC simulations. So the idea here in this problem, the idea here, what you maybe remember is that what we're doing is we propose a new gauge configuration, and then we reject this. So which means basically if it's freezed out, this proposal, this proposal of a new gauge configuration cannot change the sector anymore. So the idea, or one of these ideas, to start to make a proposal of U prime by starting from a random field configuration. So this is basically shown here. So so the idea is basically, if we, so usually in the HMC we start from a configuration and integrate this configuration through the field space towards a new point, and then we hope that this is decoupled from each other. But if we have large autocorrelation, they are basically quite similar to each other. So, but if we basically improve, if we propose a new gauge configuration starting from a different point, maybe a randomized field, and if you have a map from the randomized field towards our target space, this might solve this problem. So, but for this, we need basically to have, first of all, a good description, a good map. A good way to map from the random distribution to our target distribution. That means we not only need to know the way from going from here to here, but we also need to know how the measure of how the distribution itself is changing going from here. So we need basically to monitor or calculate the Jacobian of this transformation. So basically, if we change the fields from Z to phi, we need to calculate the Jacobian. There is a way, or there are different ways to do this, but one way is to use for this map coupling layers, which basically takes some part of our degrees of freedom and updates them with another part of our gauge links. And if we construct these kind of coupling layers such that the Jacobian is easy to calculate, and even maybe also easy to calculate the inverse of it, then we can maybe use basically neural networks. Then we can use neural networks to train these maps and find a good way. Train these neural networks such in a way that these maps map into our target field space. Okay, so there is basically this were done in low dimensional models in 5^4 in U1, which is basically which I basically take here from this paper to do it also here in the Schwinger model, and then this was done in higher fields and in higher gauge fields with SO2 and SO3. So okay, so basically let's go here. So basically, the idea is basically to have couple of, here you see, you have basically to go from this distribution to this distribution, you have a lot of different coupling layers, which comes with this transformation, which basically, this is here in the 5^4 model, leaves this fields are kept constant, while these fields are changed by using functions of these fields. And the neural networks are then basically given by these TIs and SIs. So in case of gauge theories, we need to keep gauge invariance we need to one way, we have gauge symmetry. One way is to let the symmetry exact. And due to that, we can do this by basically creating maps of gauge links which will be changed. So these are the red points here. Then gauge links which get basically plaquettes which get changed, but which we don't touch, and gauge links which we can use to as inputs for these neural networks. So yes. So this neural networks consist of basically a convolutional kernel of size 3. They're using these frozen plaquettes as input values, and usually what we're using here is using 2 hidden layers with 8 nodes each, and if we have 8 of these coupling layers behind each other, we have a full update of all gauge links in our lattice. Okay, so let's take a look to the training of using that. So so what we see here is I use 64 coupling layers. Then if you remember, what the problem is that the topological charge is not fluctuating. So the topological charge is stuck to one sector in the HPC. So we would like to have at the end, I mean, we start from a random field here. We want to project into something where we have a lot of topological sectors here also. And okay, this is just the Jacobian. So if I play this, it trains quite fast. So actually, this is our target plaquette. And after 13 steps, we are basically already there where we want to be. And you see that topological charge is actually at the beginning it's very random, but then it freezes basically out, but it can visit all different sectors here. So it basically works. So maybe I start again. So you even after one count, the plaquette is already the map is already quite good trained. So if you play it, you see that now it gets fine-tuned basically. That this map is getting smaller and smaller here. This region, you have only smaller fluctuations here during the projection. Okay, so the problem with these models is that if you increase the volume, then the acceptance rate, then the acceptance rate breaks down. So what is shown here? So basically, here is a training time plotted against acceptance rate for different lattice sizes. So these are a square lattice L 8 times 8 towards 32 times 32. And what I tried to scale the degrees of freedom in the networks with the lattice size. So I tried to scale the coupling layers and the hidden layers such that if I increase the lattice by a factor 2, that I also increase this degrees of freedom which I have to train by a factor 2 or even more. What you see is basically that the acceptance rate breaks down to going to larger volumes, and it takes longer and longer to train. So these are the 8x8 lattice, which you get something like 30% acceptance rate after 4 hours, after I think it's in seconds after. After 2 times 10 to the minus 4 seconds. But if you then go basically to 12 cube, which are these 2 points, it's rather hard to go to 30%, and then with 16 cube or even with 32 cube, it's rather hard to reach at least 5% of acceptance rate. So the idea to overcome this is basically to use domain decomposition. So before this map was done on the whole lattice. Now the idea is to basically decompose the lattice in smaller parts, and then just do this mapping on localized on each of these domains. And this is basically possible with our action, because the action itself is quite localized. And then if you basically, the degrees of freedom at the boundaries are changing. So if that can be taken into account in your proposal, if you can learn this, then you can easily go to larger volumes, because this block doesn't depend on this block. If you freeze, basically this block doesn't depend on this block if you freeze the boundaries, because the interactions are not so far from each other. Okay, so I basically did this. So freezing the boundaries of each domains. changing a bit some of the parameters like the batch size or the number of iterations. So I basically changed the boundary conditions after 1,000 iterations of the training. And then you basically get a map which can take into account the boundary conditions and gives you a rather good acceptance rate for each of this domain. And then it's trivial to go to larger volumes because they're decoupling, so you can just scale it up. But if you remember at the beginning, we had these fermions in our Boltzmann factor. So the fermions are coming with a determinant of the Dirac operator, and the determinant of a matrix is a non-local mathematical function, which means domain decomposition of the determinant. So the domain decomposition of the fermions is not so easy or not so simple. So okay, so what maybe I missed to say, but all this training for this map was done for the pure gauge action. So it's basically only done for the gluons without fermions. So now the next step would be this is basically now working for these domains, so we can scale up to larger volumes, but we need to take into account the determinant. And for this, we need to work a bit. Basically, this is the Boltzmann weight. The Boltzmann weight comes with the product over the determinant of the Dirac operator times this pure gauge weight. So now we have a map which can basically sample configuration with this weight. So we need to take into account this weight, and this we can do by accept reject steps using a factorization of the determinant. So if we have the determinant of basically of the full determinant, we can decompose it into two elements in the Schur complement, which is defined here on this red, and the block determinant defined here on the pink. And then we can decompose this guy here in another way, in the same way again, by having here a Schur complement and a block here. So basically one can factorize the determinant where the local fluctuations are contained here and the long range fluctuations are contained. No, the local fluctuations are contained in the blue one, and the global fluctuations are contained in the red one. And then the idea is to do again these accept reject steps with this weight, which is quite rough. So I have to find a good way to do this, to have a high acceptance rate and to include basically the determinant into the weight. Okay, so if you do this, and if you then calculate the topological charge and make a scan in beta, you basically with this kind of algorithm, so you update a domain with a flow up proposal, and then you accept reject with a determinant. You can calculate basically the probability for tunneling of the topological charge, which is shown here. And this is basically shown for this flow DC compared to the HMC, which we saw in the beginning has this freezing. So this means that the tunneling, that we can visit other sectors, goes down. I mean, it's rarely happening for larger betas, while for this procedure where we use these flow maps, we see that basically the acceptance, that the tunneling rate stays the same. Okay, so let's take a look to this history. So here on the right side, you see the topological charge for causal lattice spacing beta equal to 3 towards fine lattice spacing, while this blue curve is the HMC. You see that basically the HMC is freezing out, while this flow GC algorithm is fluctuating quite well. Okay, but to include the determinant, you need to minimize the number of domains to accept. This results into that the plaquette is fluctuating a bit slower, as you might then see that it's fluctuating not so well anymore. So the idea to overcome this is to basically to combine this flow GC with an HMC. So you do one HMC step and then a flow GC and so on. So basically by doing this HMC step, a flow flow GC step and HMC step. And then what you basically see, so what is here shown is an autocorrelation time of the plaquette plotted against beta. The yellow points are the flow GC, this flow where you propose as a flow and then accept reject as a determinant. And the blue is the HMC, it's fluctuating here. And you see that basically you have, I don't know, a factor of 4 larger autocorrelation times here. While in case of the topological charge, the autocorrelation time of the topological charge, you see this escalating of the HMC that's just going through the roof. If you combine all this HMC with a flow step, you get this orange points, and you basically see very mild autocorrelations. Okay, here are the coefficients if you are interested. Okay, so basically we can conclude more or less. So we basically tried to went through the simulation by using this basically cost breakdown. On one side we have the solver, then we have the number of steps, and it's the statistical error, which basically suffers from autocorrelations. So before we basically started all these simulation efforts, we had this cost scaling for the HMC, which is given by this formula. So we had a mass dependence here. And okay, this is the autocorrelation. So if you now include the multigrid and the higher order integrator, you come up with this. So basically you get rid of the mass dependence more or less. And due to higher order integrators, you also reduce the autocorrelation time here. Actually, and 1A is coming from mu. So if you get rid of the Quark mass dependence, you also get rid of one of these A's. Okay, and then the question is, I mean, this flow GC was just for the Schwinger model as a two-dimensional model, so it was not for the full QCD. So one has to still apply this model to, or this approach to full QCD. But if you can do this, if it's possible, then this you will get basically, we will also reduce this autocorrelation here, which will enable physical point simulation below this critical lattice spacing. And okay, the generated ensembles which I showed are basically now used for other measurements and will produce high precision results, which are on the way. So thank you for your attention, and yeah.
Thank you, Jakob, for your presentation. If there's any questions, Professor Alexandru, you've got your hands raised. Go ahead.
Yeah, Jakob, thanks very much. Maybe for the people who are not in this field, you should really, I don't know if you have the plot, show the worldwide simulation status, because maybe people don't appreciate that, you know, this is a global problem in HMC. It's not just a problem of our formulation. I don't know if you have the plot that we usually show.
I think I missed this plot actually. I mean, we just updated it, but I didn't include it in the.
Yeah, you just updated for me for my talk, but you didn't show it here, right?
Yeah, kind of, yeah.
Okay, I mean, just a comment here for the people who are not in this field. I mean, these configurations are there are only 5 collaborations that can do this kind of simulations, and they all have a same cutoff, namely at 0.05, nobody can simulate. So what Jakob is doing here would be really a breakthrough. In particular, because the closer are to the continuum limit, the more accurate your predictions are. And in order to discover new physics, which is what all we are after, precision is one of the criteria. I mean, some of the quantities that we are looking at are measured very precisely. So going very close to the continuum limit, so having simulations smaller than 0.05 Fermi would be critical for some of the things we are trying to compute precisely. just to make this comment for people that are not in this field. So I think this is a frontier research that it's been undertaken in the community. It's a very new area of research, and there are very intense discussions and workshops, etc., on how to solve this critical slowing down using some of the ideas that Jaco presented. But Jaco, I have a question.
Mm-hmm.
So in this combination that you have done, the last one, HMC plus the flow,
yeah,
I'm not sure I understood fully.
mm-hmm.
So you get this brown points by doing what exactly?
Actually, by combining, I mean, not combining, basically by doing one HMC step, one full HMC step. So basically you start with generating the conjugated momenta, and then you do the trajectory and accept reject step. After this, basically I do a full flow GC step. So by starting with a flow proposal and then accept reject the determinant of the by doing this the accept reject step to the determinant, a full step of this, and then again start with an HMC step. So you basically, each of these steps are fulfilling literal balance. So a combination of both, I mean, both steps are basically full Markov chain steps, simulation steps, which are fulfilling literal balance. So you can combine both to get another combination of an algorithm.
And what kind of lattices are here? Are these what we are talking about here?
Okay, so this is basically a high, I mean, to get the autocorrelation time, I did a lot of trajectories. Actually here I keep the lattice size the same. So it's 32 by 32. So it's a stringer model.
Okay.
So basically I minimize, I mean, towards the continuum, I minimize the volume. So I actually should increase here the volume to be on a constant line of physics.
Yeah.
But it's already, I mean, it's nice to see that it's that the combination works very well, and that you basically can minimize the autocorrelation time from the HMC by just adding this. I mean, basically so the HMC step is moving all the gauge links through the field space, and the flow GC step is just allowing transitions of the topological charge. While, because it's a minimum, I mean, you just pick out, you need this distance between active domains. You cannot update all the links in one of these flow GC steps. So,
okay, very nice. Thank you.
Yeah. Any other questions for Jakob? Maybe from someone in the room, as is a hybrid event.
Yeah, Jens. Huh?
Yeah, and if you can speak in the microphone, we can't hear you. Yeah.
Thanks a lot for a very interesting presentation. I just have, I'm not at all a specialist in the field. I have some technical questions. During your thermalization process of your system, do you assign velocities from a Maxwell distribution, or and then you perform an energy minimization in order to reach a stationary state?
Yes, kind of, yes. So what we actually, now I have to go through the whole stuff here. What we actually don't have in our degrees of freedoms usually are these p values. So the p's are not belonging to the thermal of particle physics. I mean, these are auxiliary fields, so we add them afterwards. So basically, if you see the p's are only, I mean, it's basically only this Gaussian integral here. So if you can integrate them out, you get a 1. So what but we need them for doing their for doing our Hamilton to integrate with our molecular dynamics, to do our molecular dynamics, sorry. So what we're doing is we can add them at each of the beginning of the trajectory. So we generate basically them as Gaussian random numbers. So because we add them to our theory, and then we're using them to go through the field space. And what you see actually is that they're taking energy during the thermalization. They're taking the energy from the other parts. So that they're taking energies from the gauge action and from the determinant. So you can basically, if you measure their I have also a video, but it's not linked. But if you measure the plaquette action, this action here during thermalization, you would see that basically you take energy from here and put it here. And what you do is you regenerate them after each trajectory newly. So basically you take this energy out then. So this is basically by construction of this so-called hybrid Monte Carlo. The hybrid comes from the fact that you add these additional fields to your theory that you're able to do molecular dynamics. Okay, and which criteria you have in order to define your state as equilibrium one? Yeah, this is a good question. I mean, this is actually it's always a good question. I mean, also if you do the simulation, it's always a good question. At what point you thermalized? So what you basically do is, I mean, the problem of this, you have these long chains, and so you to generate a lot of statistics, you would like to have several chains. So you would, at some point, if you thermalized, you want to split up. But the time where you thermalized, you have to use your, I mean, basically your experience, and at some point you say, okay, no, it's, I mean, you usually try to have a lot of space. I mean, first of all, I don't really have it, but you see, basically, you can measure this action parts, and then the action part starts to fluctuate around a value. And at some point you would say, okay, if this interval is large enough and the fluctuation looks more or less okay, then you would say, okay, at this point you thermalized, but this is always it's based on your experience. And at the end, what you do on this configuration, I mean, you sample this configuration, you save this configuration in an ensemble, and then later you use these configurations to calculate the observables. So you basically, first of all, sample the configuration, and later you measure your observables on it. And then from the behavior of the observables, you might say, okay, there are some thermalization effects inside. So you can also have some input from this side. I mean, you see it basically also in this video, but this is very extreme here. No? So what is shown here is the effective mass of the pion, which is basically, if you measure the correlation function, this correlation function basically decays with e to the power minus the mass. And if you see, I mean, I start here from a random configuration. Here the mass is very large, so it's 1, and you see that it's goes down towards a smaller number, and then it stays here. And basically, from this behavior, you would also then see that you can basically see conclude if there are thermalization effects inside or not. But in general, it's always there's not a criteria also which you can use to decide.
Okay, thanks a lot.
Okay, thank you for your question. Any other questions for Jakob? I don't see. Oh,
yeah, maybe if nobody's asking, Jakob, can I?
Yeah.
So, do you think we can extend this to realistic simulations?
Below 0.05 femtometer.
Yeah, but for the kind of lattices, and I mean, what is your feeling here?
Okay, so I don't really have a good slide, I guess, for this. Yeah.
I mean, in other words, what I'm asking is, what is the next step now?
Yes.
Right?
Yeah. I mean, then okay. I guess this kind of. I mean, I guess this kind of procedure will be the way, or one of the. I mean, one way to go forward. So you have some kind of update algorithm which allows topological tunneling. I mean, this is basically the best guess which I have in the moment, to have a HMC step, let's say, and then you have something which can change topological sectors. The question is how feasible. I mean, with this flow GC, there are some parts missing that this is working for full QCD. Especially the problem with, I mean, if you use the same procedure for the flow maps to project into your equilibrium state, you need a lot of, I mean, this volume in QCD is much larger, and so you need to find a way to train this flow that you get a good acceptance rate, and this is in the moment not really clear how to get this. But even if you have this, then you end up that the acceptance rate of the determinant will be quite. I mean, if you include the determinant, then this acceptance rate will be quite small. Yeah, and so you have to find a way how to minimize this, basically to get that this flow step basically has a large acceptance rate. Yeah, okay, so basically in the moment one can look into, I mean, what I do to figure this out is to look at, larger, look for which domains topological fluctuations are possible in QCD. And there it turns out one has to have at least 8 to the power 4. And yeah, this makes it, yeah, maybe there's a way to do brute force, but maybe this is not the best way. So basically this is quite an open question to which would be good to understand, which one needs to do some research on in order to understand how to make this possible. So yeah.
Okay. I don't see any more questions from anyone, unless anyone has one last question for Jakob. No, in which case I'd like to thank our speaker today, Jakob, for his time and his presentation. And we have another seminar next Tuesday, so next week, quantum computing applications for quantum chemistry. And we will see everyone next week. And again, thank you, Jakob, for your time.
Thank you very much for.
Bye, everyone.
Hi.
Bye.